Well, welcome back to our class on discrete mathematics as we're looking at discrete structures, mostly a focus on computer science. And we're continuing to make some good progress as we go through Rosen. And so for this chapter, we're going to be talking about discrete probabilities and get into some useful information there that will help us to characterize some additional things that is useful in number theory and how we can be applying it for applications, which has been the area that I've been trying to focus as we go through this material. So here are some things that we'll cover. We'll give an introduction to discrete probability. We'll talk about probability theory, Bayes' theorem, and then two concepts, expected value and variance. So combinatorics and probability theory share common origins. The theory of probability was first developed more than 300 years ago when certain gambling games were analyzed. And so that was the impetus, but it sure has a lot more possibilities of what it can be used for. Although probability theory was originally invented to study gambling, it is now plays an essential role in a wide variety of disciplines. For example, probability theory is extensively applied in the study of genetics. We've got a chance to get exposed to that a little bit already. When it can be used to help understand the inheritance of traits, probability theory remains popular both because of its applicability to gambling, an extremely popular human endeavor, at least for some, and it's used in a wide range of disciplines. But for our application, computer science, let's focus on that. So in computer science, probability theory plays an important role in the study of complexity of algorithms. In particular, ideas and techniques from probability theory are used to determine the average case complexity of algorithms. Probability algorithms can be used to solve many problems that cannot be easily or practically solved by deterministic algorithms. In a probabilistic algorithm, instead of always following the same steps, when given the same input as a deterministic algorithm does, the algorithm makes one or more random choices which can lead to different outputs. In combinatorics, probability theory can even be used to show that objects with certain properties exist. The probabilistic method, a technique in combinatorics introduced by Hall Erdos and Alfred Renai, show that an object with a specified property exists by showing that there is a positive probability that a randomly constructed object has this property. Probability theory can help us answer questions that involve uncertainty, such as determining whether we should reject an incoming mail message as spam based on the words that appear in the message. So we can see a practical application here, determining spam messages and probabilistically coming up with a decision, an algorithm for figuring out if we're going to allow it through or not. Okay, well, let's get an introduction into probability. We'll talk about finite probability, probability of complements and unions of events, and then finally probabilistic reasoning. Probability theory dates back to 1526 with an Italian mathematician, physician, and unfortunately a gambler, Cardano, wrote the first known systematic treatment of the object in his book Libre de Ludo Alea, Book of Games and Chance. So in the 17th century, the French mathematician Pascal determined the odds of winning some popular bet games based on the outcome when a pair of dice is repeatedly rolled. In the 18th century, the French mathematician Laplace, who also studied gambling, defined the probability of an event such as the number of successful outcomes divided by the number of possible outcomes. For instance, the probability that a die comes up on an odd number when it is rolled is the number of successful outcomes, namely the number of ways it can come up odd divided by the number of possible outcomes. Namely, the number of different ways a die can come up. There are a total of 6 possible outcomes, namely 1, 2, 3, 4, 5, and 6. and exactly 3 of these are successful outcomes, namely 1, 3, and 5, those being odd. Hence, the probability of the die coming up in an odd is 1/2. So that just gives you an idea. We'll talk about this more. So in this particular section, we will restrict ourselves to experiments that have finitely many equally likely outcomes. This permits us to use Laplace's definition of the probability of an event. We will continue our study of the probability in section 7.2 after we cover this, where we will study experiments with finitely many outcomes that are not necessarily equal. We will also introduce some key concepts in probability theory, including conditional probability, independence of events, and random variables. In section 7.4, we will introduce the concept of the experiment and variances of a random variable. So some more things that we'll cover. So first of all, Laplace. And so Laplace defined a couple of different things. An experiment is a procedure that yields one of a given set of possible outcomes. The sample space of the experiment is a set of possible outcomes, and an event is a subset of the sample space. And this is how he defined that. I'll just read part of this. So if S is a finite sample space of equally likely outcomes and E is an event, it is a subset of S, then the probability E is P of E is equal to E divided by S. So you can read the rest of this here. And so some examples, an urn contains 4 blue balls and 5 red balls. What is the probability that a ball chosen from the urn is blue? So it's basically 4 out of 5. There's a total of 9 balls and 4 of them are blue. What is the probability that when 2 dice are rolled, that the sum of the numbers of the 2 die is 7? So with the product rule, we've been introduced. So we have 6 possibilities and there's 2 rolls, so that's a total of 36 possibilities. And so we just need to look at how we can get the sum of 7, and there is a total of 6 possible ways, and so it's 1/6 of the time would be how we would get that. It just gives you a little bit of perspective. So I'll just talk about this problem and then briefly just go over some of this, but not in detail in terms of the solution. In a lottery, a player wins a large prize when they pick 4 digits that match in correct order, 4 digits selected by random mechanical process. What is the probability that the player wins the prize? And you can see that this isn't a very high probability. It just shows you the disadvantage of doing gambling, so you can keep that in mind. A smaller prize is won if only 3 digits are matched. So you can see that what the probability is that. It's a little bit larger, but still I would argue it's not worth your investment. In terms of applying Laplace's definition, there are many lotteries that award prizes to people who correctly choose a set of 6 numbers out of the first n positive integers, where n is usually between 30 and 60. What is the probability that a person picks the correct 6 numbers out of 40? And you can see this is just astronomically small. And you can see that we're looking at combinations here. We can figure that out. And that's just gives you a sense of what that is. And so definitely for the people that are providing the gambling are going to be the ones that are going to make the money. And most of the time, other people will not. So we have some other examples. What is the probability that the numbers 11, 4, 17, 39, 23 are drawn in order of a bin of 50 balls? And so once again, we can see some things are fairly small in terms of those numbers, and you can walk through that here just to get a sense of that. Okay, we have a handful of charts looking at the probability of complements and unions of events. And so here is a theorem. I won't go through the proof. Let E be an event in a space S. The probability of the event not E equals to S minus E. The complementary of the event of E is given by probability of not E is 1 minus the probability of E. So we can go through some examples. A sequence of 10 bits is chosen randomly. What is the probability that at least one of the bits is 0? So every bit is either 1 or 0. So there's just have the case of when there's only 1 0 and all the rest of them are ones. And so we can come up with a solution here. You can see what that would be like. Probably let E1 and E2 be the events in the sample space S. And so the union of E1 and E2 is what is in E1, probability of E2 minus the overlapped. And so we were looking at some of that already, and Bayesian ways of looking at this can help us to be thinking about that. What is the probability that a positive integer is selected at random from the set of positive integers not exceeding 100 if it is divisible by 2 or 5? So we have a probability of divisible by 2, probability of divisible by 5, and we can work that out and come up with a solution. You can see that here. Finally, a problem even going through this, it can be a little bit confusing. They even note that here, Monty Hall's puzzle. If you are asked to select a door out of 3 doors to open, there is a large prize behind one of the doors, and if you select a door, you win the prize. After you select a door, the game show host opens one of the other doors. The prize is not behind that door, and he gives you the opportunity to switch your selection, should you switch. And so this is just a strategy of what they would say, counter to what you might think that they're that what you should do. So you can read through that, and they're stating that you should switch. Okay, so that's a little bit of a perspective on things that we're going to be talking about. Now we're going to get into some details of thinking about a lot of different useful tools that we want to make sure that we're going to consider. The probabilistic method, you can refer to Rosen. We don't have that here in these charts. So assigning probabilities, probability of complements and unions of events, conditional probability, independence, Bernoulli trials and the binomial distribution, random variables, the birthday problem, and Monte Carlo algorithms. So in the last section, we introduced the notion of probability of an event. We define the probability of event E as Laplace did, being the number of outcomes E divided by the total number of outcomes. This definition assumes that outcomes are equally likely. However, many experiments have outcomes that are not equally likely. For instance, a coin may be biased so that it comes up heads twice as often as it does as tails. Similarly, the likelihood that the input of a linear search is a particular element is a list or is not in the list depends on how the input is generated. So how can we model the likelihood of events in such situations? In this section, we will show how to define probabilities of outcomes to study probabilities of experiments where outcomes may not be equally likely. So suppose that a fair coin is flipped 4 times and the first time it comes up heads. Given this information, what is the probability that the heads comes up 3 times? To answer this and similar questions, we will introduce the concept of conditional probability. Does knowing what the first flip comes up as heads change the probability that heads comes up for 3 times? If not, these two events are called independent, concepts studied later, and we'll get to that. Many questions address a particular numerical value associated with the outcome of an experiment. For instance, when we flip a coin 100 times, what is the probability that exactly 40 heads appears? How many heads should we expect to appear? In this section, we will introduce random variables, which are functions that associate numerical values to the outcomes of the experiments. Okay, so let's talk a little about assigning probabilities. Laplace's definition from the previous section assumes that all outcomes are equally likely. Now we'll try and remove that and give a sense of how we would do that. So what we end up having is a function P from the set of outcomes of the sample space is called a probability distribution. And there's various kinds of distributions that we'll get a chance to be thinking about, like a Bell distribution. Here's an example. What probability should we assign to the outcomes heads and tails, H and T, when a fair coin is flipped? When the probability should be assigned to these outcomes when the coin is biased, so the head comes up twice as often. And so thus we can see how this would work out. Heads are twice as often as tails, and so thus it's not a balanced 50%. And so which we'll get into a ratio, so thirds is what we come up with. Suppose that S is a set with n elements, the uniform distribution assigned the probability of 1 over n to each of the elements. So note that we could have used Laplace's definition here as well. So this would be what we would have for a fair coin versus what we showed here with a biased coin in the last chart. Well, let's look at the probability of an event. The probability of an event E is the sum of the probabilities of the sum of outcomes in E. So here we can see that to give you a sense. Suppose that a die is biased so that 3 appears twice as often as the other numbers, but that the other 5 outcomes are equally likely. What is the probability that an odd number appears when we roll the die? And so here is a solution. We first have to put in this concept that there's a bias in it, and then we can come up with what we have here, and you can see how that would work. In terms of the probabilities of complements and union of events, the complement probability of not E is equal to 1 minus the probability of E still holds, since each outcome is either E or not E, but not both. So we can have this relationship that we can see how that would work. We can also do a combination of events. If E1, E2, ... is a sequence of pairwise disjoint events in the sample space, then we can be having this relationship. And I'll refer you to Rosen as well as exercise 36 and 37 to be walking through the justification for that. In terms of conditional probability, that's where we have this. Let E and F be events with the probability of F is greater than 0. The conditional probability of E given F, which is this probability E given F, is defined by this. And so and in terms of an example, a bit string of length 4 is generated at random so that each of the 16 string of length 4 is equally likely. What is the probability that it contains at least 2 consecutive zeros given that its first bit is 0? So you can walk through the solution, but they're arguing that the probability would be 5 over 8. Here's another example. What is the conditional probability the family with 2 children has 2 boys, given that they have at least 1 boy? Assume that each of the possibilities BB, BG, GB, and GG is equally likely, where B represents a boy and G represents a girl. So, and they work out the numbers here, and they say that the solution is 1 over 3. Independence, the events E and F are independent if and only if we have this relationship is true. And so suppose E is the event with a randomly generated bit string of length 4, begins with 1, and F is the event that the bit string contains an even number of 1s. E and F, are they independent if the 16-bit strings of length 4 are equally likely? And what they do conclude is they are equally likely, and you can work through this solution to convince yourself that this is a valid thing to look at. Here's another example. Assume that we saw this before, that each of the 4 ways a family can have 2 children is equally likely. And the events E, that a family with 2 children has 2 boys, and F, with a family with 2 children has at least 1 boy, independent. And you can see what they argue here. They say that the events E and F are not independent, and they can show the justification you can see. Well, what about pairwise and mutually independence? The events E1, E2, dot, 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 up to En are pairwise independent if and only if it satisfies this relationship for all pairs I and J, with I less than or equal to J is less than or equal to N. And so the events are mutually independent if this relationship holds. And so instead of just two elements, we have multiple elements. And so we can expand what we've had a chance to see before to multiple elements. Okay, once again, I'm not going to read the bio here, but Bernoulli is another example of a mathematician that is noteworthy that Rosen wants us to get a chance to be thinking about this in context. And as I said previously, the lives of these individuals have produced results, and we're standing on the shoulders of these folks as we're getting a chance to get this survey of number theory and the various things we're looking at discrete mathematics. So suppose an experiment can have only two possible outcomes, for example, the flipping of a coin or the random generation of a bit. Each performance of the experiment is called a Bernoulli trial. An outcome is either a success or a failure, and P is the probability of success, and Q is the probability of failure. And we have this that P plus Q, it has to be equal to 1. Many problems involve determining the probability of K successes when an experiment consists of N mutually independent Bernoulli trials. So as an example, a coin is biased so that the probability of heads is 2/3. What is the probability that exactly 4 heads occur when the coin is flipped several times? And so this is the relationship that we get. We have the combinations here, and then we have some other things that we include. So there are 2 to 7, 128 possible outcomes, a number of ways um, ways 4 of the 7 flips can be determined with a combination 7-4. Probability of each of the outcomes is 2/3 to the 4th times 1/3 to the 3rd. Since the 7 flips are independent, hence the probability that exactly 4 heads occurs is, and we can have this number that we've spelled out here, maybe roughly about 1/4 or so. So the probability of K successes in independent trials, Bernoulli trials. So the probability of exactly K successes is in N independent Bernoulli trials with the probability of success P, and the probability of failure is equal to Q is a failure Q, which is 1 minus P, is given by this relationship. And I'm not going to walk through the proof, but this is the value of what we're seeing there. Here's another relationship for random variables, a definition. A random variable is a function from the sample space of an experiment to the set of real numbers. That is, a random variable assigns a real number to each possible outcome. So a random variable is a function. It is not a variable, and it is not random. In the late 1940s, a couple folks, Feller and Dobb, flipped a coin to see whether both would use, quote, random variable or the more fitting chance variable. Unfortunately, Feller won, and the term random variable has been used ever since. So terminology, that's how it came about. So here's another definition. The distribution of a random variable x on a sample space S is the set of pairs that's listed here for all, for R is an element of x of S, where P of x equals R is a probability that x takes the value of R. So suppose that a coin is flipped 3 times, let KT be the random variable that equals the number of heads that appear, where T is the outcomes. Then XT takes on the following values. And you can just walk through these results that they talk about here. So I'll just go through this quickly. A birthday problem, the puzzle finds the number of people needed in a room to ensure that the probability that at least two of them have the same birthday is more than one half, has a surprising answer, which we'll find. So we assume that all birthdays are equally likely. There are 366 every day of the year plus leap year. First, we find the probability P of n that at least two of n people have the same birthdays. So you can walk through this. I'm not going to go through the details. So consequently, a minimum number of 23 people are needed so that the probability that at least two of them have the same birthday is greater than one half, or 50%. That's the bottom line. Monte Carlo algorithms, this is something that I've used, and it can be a useful tool to have in your toolbox. Algorithms that make random choices at one or more steps are called probabilistic algorithms. Monte Carlo algorithms are probabilistic algorithms used to answer decision problems, which are problems that either have a true or false as their answer. So say you have one thing that you're varying, it's only going to have one true or false. A Monte Carlo algorithm consists of a sequence of tests. For each test, the algorithm responds to true or unknown. If the response is true, the algorithm terminates with the answer true. After running a specified sequence of tests where every step yields a known, the algorithm outputs false. The idea is that the probability of an algorithm incorrectly outputting false should be very small as long as a sufficient number of tests are performed. So you come up with a design, a scenario, and you're trying to kick the tires and see if it consistently always gives the correct result or not. So you can be seeing how that would be useful for algorithms. So probabilistic primality testing, this is an example 16 in Rosen, is an example of a Monte Carlo algorithm which is used to find large primes to generate the encryption keys for RSA cryptology. And so we talked about this in chapter 4. Some of you hopefully got a little bit more interested in cryptology as a result of us going through that information. An integer n greater than 1 can be shown to be a composite, that is, it's not prime, if it fails a particular test, which is Miller's test, using a random integer b with 1 is less than b less than n as the base. But if n passes Miller's test by a particular base, and many may either be a prime or composite. The probability that the composite integer passes n Miller's test is for a random b is less than 1/4. So failing the test is the true response in a Monte Carlo algorithm, and passing the test is unknown. If we perform the test k times, choosing a random integer b each time, and the number n passes Miller's test at every iteration, then the probability that the composite is less than 1/4 to the k power. So for a sufficiently large k, the probability that n is composite, even though it has passed all k iterations of Miller's test, is small. And as an example, with 10 iterations, the probability that n is composite is less than 1 in a million. Okay, so that just gives you some useful information, some things that we want to be exploring concerning probability theory. Now let's talk about Bayes' theorem. So we'll talk about his theorem. We'll talk about a generalized Bayes' theorem, how we can be using Bayesian spam filters. We've already mentioned spam filters a little bit. It also has applicability to AI, but we're not going to be covering that in this lecture. See Rosen for more details on that. There are many times when we want to assure the probability that a particular event occurs on the basis of partial evidence. For example, suppose we know the percentage of people who have a particular disease for which there is a very acute diagnostic test. people who test positive for the disease would like to know the likelihood that they actually have the disease. In this section, we introduce a result that can be used in determining the probability, naming the probability that a person has a disease given that a person tests positive for it. To use this result, we may need to know the percentage of people who do not have the disease but test positive for it, and the percentage of the people who have the disease but test negative for it. Similarly, suppose we know the percentage of incoming email messages that are spam. This gets into this application. We see that we can determine the likelihood that an incoming email message is spam using the occurrence of words in the message. To determine this likelihood, we need to know the percentage of incoming messages that are spam, the percentage of spam messages in which each of these words occurs, and the percentage of messages that are not spam in which each of these words occurs. The result that we can use to answer questions such as this are called Bayes' theorem and dates back to the 18th century. In the past 2 decades, Bayes' theorem has been extensively applied to estimate probabilities based on partial evidence in areas as diverse as medicine, law, machine learning, engineering, and software development. So a lot of things to be mindful of. What's the motivation for Bayes' theorem? It's Bayes' theorem allows us to use probability to answer questions such as the following. Given that someone tests positive for a particular disease, what is the probability they actually do have it? We already mentioned that, but let's just see that here in more detail in this chart. Given that someone tests negative, what is the probability that they actually don't have it? So Bayes' theorem are applicable in many areas, and we already got a chance to think about that. So is it a true positive or a false negative? These are things that we can start to identify. So here's Bayes' theorem. Suppose that E and F are events from a sample space S such that the probability of E is not 0 and the probability of F is not 0, then we have this relationship. So if we have 2 boxes, the first box contains 2 green balls and 7 red balls. The second contains 4 green balls and 3 red balls. Bob selects one of the boxes at random, then he selects a ball from that box at random. If he has a red ball, what is the probability that he selects a ball from the first box? So roughly 0.6, a little bit more than 6, little bit more than half for sure, 65% just about. So we can look at the derivation of Bayes' theorem. So I'm not going to walk through this, but you can see Rosen's for some more details about that. And here's some more things in terms of the derivation of Bayes' theorem, so I'll skip over that. And then we have one more slide that gives us more information about the derivation of Bayes' theorem. Okay, very useful, but for the sake of time, I'm just going to keep this high level and not walk through that definition and that proof. What about it? Using Bayes' theorem? Suppose that one person in 100,000 has a particular disease. There's a test for the disease that gives a positive result 99% of the time when given to someone with a disease. When given to someone without the disease, there's a 99.5% of the time that it gives a negative result. So we want to find the probability the person who tests has the disease, a true positive, and and vice versa for the second case. Probably a person who tests negatives does not have the disease, a false negative. So should someone who tests positive be worried? And so how can we look at those values? So here is the solution, and you can see that these values are relatively small. So you could argue that it's a good testing method. So this is if it's positive, and then if it's negative, and so we can see that you can see that it's doing even better for the negative case. We can generalize Bayes' theorem to more than to greater numbers. And so suppose that E is an event from a sample space S such that F1, F2, all the way up to Fn are mutually exclusive events such that we have this relationship, assuming that the probability of E for all cases is not equal to 0. And here is that generalized relationship. And if you go to exercise 17, you can work through that proof on your own. Okay, well, we had this application. What about Bayesian spam filters? How do we develop a tool for determining whether an email is likely to be spam? If we have an initial set B of spam messages and get G of non-spam messages, we can use this information along with Bayes' laws to predict the probability that a new message is spam. We look at a particular word W and count the number of times that this occurs in B and G. And so we have these relationships. And B of W and then G of W, we want to estimate the probability that a message contains W, and we have this relationship, and estimate the probability that the message is not spam, and so we'll be using that relationship. So we'll work through this example here, and here are some of the developments. So let S be the event that the message is spam, and E is the event that the message contains the word W. And so we come up with some values here. There's also one of the exercises that in Rosen that you can look at this in more detail. So this is a practical example that we can look at that can be helpful for us. Let's go ahead and give an example more hands-on. We find that the word Rolex occurs in 250 out of 2,000 spam messages and occurs 5 times out of 1,000 for non-spam messages. Estimate the probability an incoming message is spam. Suppose our threshold for rejecting the email is 0.9. And so we class the message as spam and reject the email. So if it has, this is the case that we have that we can consider. Maybe that's a good way for us to be determining whether or not it's spam. At least it's one approach, and so we're getting a chance to be thinking about that. Well, what if we looked at it for multiple words? So the generalized way of having Bayesian approaches, accuracy can be improved by considering more than one word as evidence. Consider the case where E1 and E2 denotes the events that the message contains both W1 and W2. And so we have these relationships that we can be utilizing. And as an example, now when we have 2,000 spam messages, 1,000 non-spam messages. The word stock occurs 400 times in spam, 60 times in non. The word undervalued occurs 200 times in spam and 25 in non. So then we have with this specific example, we can walk through this that we can get a decent way of determining how likely a message is spam with these two words. You can walk through this solution. And here's just a little bit more. In general, the more words we consider, the more accurate the spam filter with the independent assumption if we consider keywords. So we can further improve the filter by considering pairs of words as a single block or certain types of strings. Okay, so a lot of good information that we got a chance to be thinking about. Now let's talk about expected value and variance. And so some of this may be familiar to you. You may want to pause it and think about this a little bit more, but I'll try and keep things at a high level to have us get a general sense of what we're trying to add to the table for our discussion about discrete structures, discrete mathematics. So here's what we'll talk about in more detail: expected value, linearity of expectations, average case computational complexity, geometric distribution, independent variable, random variables, variance, and finally Chebyshev's inequality. So the expected value of a random variable is the sum of all elements in the sample space of the product of the probability of the element and the value of the random variable at this element. Consequently, the expected value is a weighted average of the values of the random variable. The expected value of a random variable provides a central point for the distribution of values of the random variable. We can solve many problems using the notion that the expected value of a random variable, such as determining who has an advantage in gambling games and computing the average case complexity of algorithms. Another useful measure of a random variable is the variance, which tells us how spread out the values of the random variable are. We can use the variance of a random variable to help us estimate the probability that a random variable takes the values far removed from its expected value. We'll get a chance to be thinking about that. The expected value or expectation or mean. So the mean might be a word that's more familiar to you of the random variable x of s, and the same space is given by this. So it's a summation of the probability of each event times that element of the what we're looking at. So so if we have a fair die, we can see this. Let x be the number of the outcomes when a fair die is rolled. What is the expected value of x? The random value x takes a value of 1 all the way up to 6. Each has a probability of 1/6, so it comes up with this. So we have this value, so we get a total of 21 over 6. Divide that down, and we get a total of 7 divided by 2. If x is a random variable and p of x equals to r is a probability that x equals r, then we have this relationship. And so this is a proof for that. I'm not going to walk through that, but you can see Rosen for more details. The expected number of successes when n mutually independent Bernoulli trials are performed, where the probability of success on each trial is equal to P is equal to NP. And so here is the proof for that. And you can pause and think about that. Here are some more details for us as we think about this and work out some of the details. Linearity of expectations. The following theorem tells us that the expected values are linear. For example, the expected value of the sum of random variables is the sum of their expected values. We can see that listed out here, breaking it down into elements. And so if x sub I is with I equal to 1 all the way up to n, with n as a positive integer or random variables on S, and if a and b are real numbers, then we get this relationship. And you can see Rosen for the details of the proof. What about linearity of expectations? So I won't go through this in detail. Expected value in the hatchet problem. A new employee starts a job checking hats, but forgot to put the claim check number on the hat. So the end customer just receives a random hat from those remaining. What is the expected value of the hat returning correctly? And so this is the answer, and surprisingly, the answer remains the same no matter how many people have checked their hats. So now we're getting into some areas where maybe you have to sit and think about this a little bit more. What about expected number of inversions in a permutation? The order pair ij is the inversion in a permutation of the first n positive integers if I is less than j, but j precedes I in the permutation. Here is an example. There are 6 inversions in the permutation 35142. Find the average number of inversions in a random permutation of the first n integers. So I'll let you review that, but this is another area that you can start to be exploring with this type of um, number theory type of effort. Okay, the average case computational complexity. The average case computational complexity of an algorithm can be found by computing the expected value of a random variable. Let the sample space of experiments be the set of possible inputs A of j, where j is 1 all the way up to n, and let the random variable x be the assignment to A of j of the number of operations used by the algorithm when given A of j as input. We can assign a probability of P of AJ to each of the possible input values A of j. The expected value of K of X is the average case computational complexity of the algorithm. Now we can be looking at the average case complexity of a linear search. And so this is where we get a chance to be practical. What is the average case complexity of a linear search? If the probability that X is in the list is P, and that is equally likely that X is any of the n elements of the list. And so we have our pseudocode, and so we can actually compute the average case complexity using this information. Here is the solution, and I'll let you feel free to pause the video and go over that in more detail, but I'll just skip over this for now. What is the average number of comparisons used by the insertion sort from chapter 3? And so now we can be thinking about that. That's the insertion sort. We have the linear search, and we have the tools of which we can be figuring out the average case complexity. So we have two algorithms, and we can figure out the average case complexity as we're looking at this. Here it is for the insertion sort. A little bit more information on the insertion sort. Then we have the geometric distribution. The random variable x has a geometric distribution with parameter p. If p of x equals k is equal to the quantity 1 minus p to the k minus p times p for k equals 1, 2, 3, etc., where p is real numbers with 0 is less than or equal to p is less than or equal to 1. So I'll let you review that. That just gives us some more information for us to be thinking about to answer that problem. Okay, just continuing on here. So we talked about the geometric distribution. We can have independent random variables. The random variables x and y on a sample space S are independent if we have this relationship. If x and y are independent variables on a sample space S, then the expectation of xy is equal to the expectation of x times the expectation of y. Then we have variance, and so variance is the expected value of the square deviation from the mean of a random variable. So the deviation of x, where S is an element of the set S, is x of x minus e of x, the difference between the value of x and the mean of x. Definition here, let x be a random variable on the sample space S. The variance of x denoted by v of x is equal to that equation. That is, v of x is the weighted average of the square of the deviation of x. The standard deviation of x denoted by sigma of x is defined to be that. If x is a random variable on the sample space S, then v of x is equal to the expectation of x squared minus the square of the expected value of x. So some interesting information there for us to be thinking about. we have a couple of examples. What is the variance of the random variable x, where x of t is equal to 1 if a Bernoulli trial is success, and x of t is equal to 0 if it is a failure, when p is a probability of the success and q is a probability of failure. That's an example here. You can read through the solution of that as you would like. I'm just going to skip over this. This is a formula that is in Rosen that you can feel free to look over. And I'll just finish up with this one last thing, Chebyshev's inequality. And what this does, it provides an upper bound on the probability of deviation of a random variable with finite variance from its mean. And so thus we can come up with an upper bound, and this can be useful for us to be trying to characterize how well something is performing, and this is the upper bound that we're getting a chance to be exposed to. All right, thank you very much. Have a good day.